All right. We're going to get started on today's lesson. It is Thursday, December 3rd, 2020. We're continuing in section 5.3, conditional probability and independence. And today's topic is going to focus on the general multiplication rule and tree diagrams. I find tree diagrams to be incredibly helpful when looking at like a sequence or series of events that are connected and their probabilities. It's a very visual way of looking at these things that helps connect the right numbers to the right things. So I really like these. So first, here's the general multiplication rule. Right, the probability that events A and B both occur. Let's get a pointer here. Can be found using the general multiplication rule. Right, the probability of A and B, which we can write symbolically as the probability of A intersection B, is equal to the probability of A times the probability of B given A. Right, and this is just a reworking of our conditional probability rules. All right, our conditional probability uses the rule that P of B given A is equal to the probability of B and A divided by the probability of A. Right? So this is just rearranging this equation, right? We multiply each side by probability of A, right? And we get the probability of A times the probability of B, A, B given A equals probability of B and A, right? So it's just a reworking. So this is our general multiplication rule. Looks a little weird. However, once you see the tree diagrams and how it's actually connected, it makes a lot of sense, at least in my opinion. All right? So, see, we need a moment to write down this new rule. Yes, okay. Let's make a note that that's what this rule is up here. It's our conditional probability rule. So now, let's look at an example. All right? We have this, the Pew Internet and American Life project find that 93% of teenagers ages 12 to 17, right, use the internet, and 55% of online teens have posted a profile on a social networking site. So we got a couple of percentages. We got a 93%, 5%, right? We want to find the probability that a randomly selected teen uses the internet and has posted a profile. So let's look at the information that we know. All right. We have two events that we're considering. We have uses the internet and posted a profile. Let's call this guy A. We'll call this one B. All right. We have 93% of teenagers use the internet. So that means the probability of A is 0.93. All right. And 55% of online teens have posted a profile on a social networking site. Right? We don't know the probability of B at this point because this is connected to them being online using the internet. Probability of B given A is 55%. All right. Are you guys following how I was able to pull these two probabilities out of the context? I hope so. Yes? Okay, Jocelyn says yes. All right. Yes. All right. Thank you, Daniela. All right. So again, reading the problems, identifying our events, and kind of identifying the probabilities that are known before actually starting to answer the problem can be incredibly helpful, incredibly important. So now we're trying to find the probability of A and B, right? Based on our new rule, we know that this should be equal to probability of A, right, times the probability of B given A, which we have. We have those two numbers, all right? The other thing to remember is probability of A and B is the same probability of B and A. Those have the exact same probability. Just because we switch B and A on either side of the and doesn't change what the value is. Right? These are equivalent. Probability of B and A is the same as probability of A and B. Right? So this gives us 0.93 times 0.55, which at that point we grab our handy dandy calculator. And it tells us that the probability is 0.5115. Or 51.15%, or we can say it's approximately 51%. And we're done. Right. So again, in my opinion, the key on this problem was identifying the probabilities we knew first. So that allows us to set things up properly. If we had misinterpreted this as knowing the probability of B, right, it would have made this kind of impossible to solve because we don't have any actual numbers, we don't have a Venn diagram, we don't know what the intersection of A and B is if all I was given the probability A and probability B. So just that. Any questions or anything I can clarify? Move on to our next thing, which is a tree diagram. All right, tree diagrams help us apply the general multiplication rule while creating a sample space that models the chance process that involves a sequence of events. So in general, right, we have essentially like a start point. And there may be two possibilities. And they'll have some probability associated with them. We'll say like 0.8, which would mean this has to be the rest. There's only two choices. They have to make up 100% of the probabilities, right? So we can say like this is choice 1, choice 2. And let's say that of these, there's two more options. Like maybe it's like a yes or no. And this has maybe a 0.6 and a 0.4, 0.3, 0.7, right? So this is essentially what a tree diagram looks like. It's a way for us to fill in different sets of probabilities if we know what one is, one choice. Like if I know that 80% of the students wear sandals to school, that would imply 20% do not, if that's the only information given. All right. So that's the basics of how to set up a tree diagram. All right. It shows a series of options that go in sequence. All right. So, any questions so far? We'll do a couple examples that will make this much more applicable and understandable. All right. And we need a moment to write anything down or draw anything or anything at all. Yes, okay, I will pause. All right, so let's look at our example here. So, Mr. Mosley hits the snooze bar on his alarm clock on 60% of school days. All right, likes his sleeping in the nice warm sheets. All right, if he doesn't hit the snooze bar, there's a 0.9 probability that he makes it to class on time. However, if he hits the snooze bar, there is only a 0.7 probability that he makes it to class on time. On a randomly chosen day, what is the probability that Mr. Mosley is late for class? All right, so let's get our stuff together here. We have a 60% chance here. We've got a 0.9. We've got a 0.7. All right, so we have the alarm, right? Choice one is snooze, right? Or we'll call the other one wake, right? We have 60% chance that I'll hit the snooze button, which means there is a 0.4% chance that I just wake up. All right. And then if I snooze, there's two choices here. On time or late. We have on time or late. Right? So if I snooze, let's do this. If I don't hit the snooze bar, there's a 90% probability that I make it to class on time. So that means if I wake up, I have a 90% chance of being on time, which leaves only a 10% chance to being late. If I hit the snooze bar, there's only a 70% probability I make it to class on time, so that's a 0.7, leaving a 0.3% chance that I'm late, or 0.3 probability that I'm late, 30%. All right, and we want to know what is the probability that I am late for class. All right, so we've got to put these things together. There are two paths, so to say, that lead to me being late for class. All right. We can snooze and be late, or wake up on time and be late. All right. So there's two paths through the tree that get us there. This means All right. Yes, Matthew.
I just had a question. Where did you get the 40%?
Okay. So we know that I have a 60% chance of hitting the snooze button, right? So I have a 40% chance of not hitting it, right? Because those are the two options. I can either hit the snooze button or I can wake up. So it has to add up each like branches off of a single event have to add up to 100%. Since I have two branches, two options, I need these two to add up to 1, 0.6 plus 0.4. Then I have the 0.7 and 0.3, 0.9 and 0.1. Does that answer your question?
Yes, thank you.
Okay, you're welcome. All right, so now we have, again, we have the 60 and the 30. And then we have the 40 and the 10. So these are the things that I'm going to add up, so to say. Now, we have our two options. We are trying to find, probability. I'm late. Okay. This is going to be equal to the probability that I snooze and I'm late plus the probability that I wake up. Oops. Helps if I can write. And I'm late. All right. Based on the general multiplication rule, we have snooze and late is equal to the probability that I am late, right? Or probability that I hit snooze given, or probability that I'm late given that I hit snooze. Which, the long and short of it is I multiply these two probabilities. We have 0.6 times 0.3 is the probability that I hit snooze and am late. I follow the branches. Right, we go here, and then it says, okay, well, if I hit snooze and I'm late, I follow there. If I wake up on time and I'm late, I follow this branch. So I multiply those two things together. So over here we have 0.4 times 0.10. And again, this is based on that general multiplication rule where we know the probability that I'm late given that I hit snooze, right? And I know the probability that I hit snooze. Okay. Does everyone understand why I'm doing these two pairs of multiplications? All right. So the probability that I am late for class is about 22%, or 0.22. What questions do you guys have about this example? What can I clarify? Okay, see, we need a moment to write anything down from this example. So now, same problem, different question. Now we want to know, suppose Mr. Mosley is late. So we already know that I'm late. What's the probability that I hit the snooze bar that morning? Right? So we already know, right? Probability of being late, which we just found was 0.22. This question is asking what's the probability that I hit snooze given that I was late. Right, on the previous one, the probabilities we knew was the probability that I was late given that I hit snooze. Now we're finding another probability here. Right? So we have probability I'm late, 0.22. I want probability of snooze given that I was late. We know, because of our previous rule, probability that I hit snooze given that I'm late has to be equal to the probability of snooze and late divided by probability of being late. Right? So now we're going back to the previous conditional rule that we have. Right? So, what do we know? That we have this and, right? What do we do from here, guys? What can we fill in?
Would late be 0.22?
Yep. So we can fill that point in, right? 0.22. How do we get this snooze and late? Look back at what we have here, right? We already have that number, right?
Would it be 60 and 30? Like 60 being snooze and then 30 being late?
Yeah. So it's that same like branch of multiplying here, snooze and late, right? We have that 0.6 times 0.3, which gives us that 0.18. So again, when we come back here, right, the snooze and late is that 0.6 times 0.3, which we get from our tree diagram. So we get the 0.18 divided by 0.22, and that gives us an answer, which my calculator will tell me. 0.81818181. So we'll say 0.81. So we could say maybe about approximately 82%. there we have it. So, yeah, what questions do you have?
Mr. Mosley,
Mm-hmm.
for the last problem, we didn't use like this rule, right?
Let's see, on the like previous page problem?
Yeah.
No, we use the general multiplication rule.
So like, how do we know like to use like the general multiplication rule on like that problem again, and then like using like another rule on this problem?
So it comes down to reading the problem very carefully, and like I said, identifying the probabilities you know and what you're trying to find, right? In this first problem, we saw the question saying, what is the probability that I'm late, right? So that's this probability, right? Probability of late. There's two ways to be late, right? And so the general multiplication rule is telling me to multiply, right? P of, A and B, P of snooze and late is the multiplication of the probabilities of those two things occurring in sequence, this times this, 0.6 times 0.3. That's essentially what the general multiplication rule tells us to do. If we look back one more time, just to the rule in general, right? A and B equals probability of A times probability of B and A, right? So what we found is the A and B, right? Probability of A times probability of B given A. When we look back at our tree diagram for this example, I know I'm flipping around a lot, this is the probability, right? The 0.3 is the probability of L given snooze, right? Late given snooze, so to say. So the probability of A, S and L is the probability of those two things multiplied, right? The probability of L, or probability of S, times probability of L, essentially, or probability of, I'm stumbling over this, but I'm not sure if this is helping or not. Give me a second. Fitting here. So let's look at this. So going back to your initial question, how do we know when to use which rule, right? The good news is they're essentially the same set of things, right? The general multiplication rule is just a reworking of the conditional probability rule. It's just, I'm rearranging it based on the thing that I need, right?
Oh, okay, I see.
See? So when we said probability of being late, right? That's so in our conditional probability, right? We had probability of being late. So we have two events. Being late, and we have probability of hitting snooze. These are the two defined events. So we'll call this one L and this one F. The conditional probability says the probability of being late, given that I hit snooze, right, is 0.3. Right? That's this right here. So when I'm trying to find the probability of being late, the other thing that we know is the probability of snooze, right? This is 0.6. So if I set up the conditional probability, P of L given S has to equal P of L and S divided by probability of S. We rearrange that right? We get probability of S times probability of L given S equals the probability of L and S, right? So this is that rearrangement, and this is our general multiplication rule. So that's why this, right, the 0.6 times the 0.3 ends up here, right? It gives us these numbers. We get the L and S, which is what we needed. That's the one path is hitting snooze and being late. The other path, you know, probability of waking up and being late, which are complements, so we don't need other events, but I don't want to do the notation for that right now. It could be a little more confusing. So that's how we get that point. Then when we go to the next question, we're looking at just being late, right? And so because there's certain pieces we know already, right? The previous one was late given snooze. Now we're doing snooze given late. Can't, if they're not equivalent, right? So I fill in the stuff I know, which I know that the conditional probability says this must be true. And we have the fact that snooze and late, right, is equal to probability of late, or sorry, probability of snooze and late is equal to the probability of late and snooze. Those are equivalent. So that allows me to use the results from the previous part of the problem.
Okay, I think that kind of makes sense. So you're just like you're just kind of tailoring like the other like equation or the other formula to make it like fit for this problem.
Yes.
Okay, thank you so much.
You're welcome. And sorry if it was a little confusing. I know it's, when we start getting all this notation and then like reading the problem and properly identifying things can be incredibly confusing when you first start. I remember doing this stuff in the probability class I took in college, and it was very confusing the first time I tried to do it. So I can relate. So, yeah. All right. I'm glad I can help. So now, we're going to do another example. So, excellent. All right. Let's see. Yeah. Okay. Okay. Real quick, before I start the example, technically we're at 40 minutes right now. This example is probably going to take 10 minutes or so to work through. You guys want me to do the example? You guys okay staying
Yes,
on the...
please.
I'm sorry?
I said yes, please.
Okay. Okay. I've got one yes. I don't hear anyone saying no so far. So here's what we're going to do. This whole thing, problems here. Excellent. I've got it in OneNote because I don't have enough space to work through the whole problem here. So we're going to jump over to OneNote. So we can work this bad boy out. So here we go. We have the Kaiser Family Foundation recently released a study about the influence of media in the lives of young people aged 8 to 18. In the study, 17%. So the youth were classified as light media users. 62% were classified as moderate media users. 21% are heavy media users. And then of the light users, 74% describe their grades as good. 68% of the moderate users have good grades, and 52% of the heavy users. So we've got a few different bits of information. Go from light, moderate, heavy again. Suppose that we selected one young person at random, right? So we're going to draw the tree diagram. So we're starting with our, say, we'll just say teens here. Right, and we have 3 options. So this one's going to have 3 original branches, right? And we get to classify those as light, right, moderate, and heavy. Light is 0.17. Moderate is 0.62. And then heavy, right, we have 0.21. Right, so again, if we add these up, right, 0.62 plus 0.17 plus 0.21 gets us to 1, 100%. So that's good. Then our next branch, for each of these, we have 2 branches, right? We have good grades, bad grades, right? So we'll just say good, bad, good, and bad. Good and bad. So now the light users, 74% describe their grades as good. So we have 0.74. Leaving, 0.26 for bad. We have 0.68 of the moderate users for good, which leaves us 0.32 for bad, and then 52% for heavy, leaving us with 0.48 for bad. So this is our tree diagram. This is now, the nice thing with the tree diagrams is it gives us that sample space. We don't have the data, we can't make a two-way table. So this gives us that enough information where we can solve things now. We have all the little bits and pieces we can get. So this is A. B, find the probability that this person describes his or her grades as good. So we're finding the probability of good, right? So probability of good has 3 routes, right? I can go through light and then to good. We can go moderate to good and heavy to good. All right. So again, we have P of light and good plus probability of moderate and good plus the probability of heavy and good. All right. And based on what we've done so far and what we've seen in our previous examples so far today, to get P of probability of light and good, I multiply these two numbers, 0.17 times 0.74. plus 0.62 times 0.68 plus 0.21 times 0.52. Right. If you're not following how I got these numbers and how I've set this up, please say something or raise your hand or something. If this is not making sense, please let me know in some way. Okay. So then at this point, we get our handy dandy calculator back out. Yes, Matthew.
So yeah, you just did today. That's what's going to be in for the discussion board for today.
Yes.
Oh, okay, that was just my question.
Got it. All right, and we get 0.6566. Right, which we can, convert to a percentage. Right, this could be 65.66%, or we could say it's approximately 66%. But anyway, that's the result for part B. Now, part C, given, remember that's a buzzword now. The person describes his or her grades as good. We have given good. What is the probability that he or she is a heavy user of media? So this is probability of heavy given good. Right. So again, properly identifying the thing that we're finding is going to help us work through the problem here. Scroll up a bit. That should be good. So let's look at part C. Again, we're finding probability of heavy given good. All right. Now we know again that this is equivalent to the probability of heavy and good divided by probability of good. And this is our conditional probability rule. We have all these numbers, hooray! Right? So we have probability of good. That's the one we just found. Probability of heavy and good is this right here. So now we fill in our blanks. Not our blanks, so we fill in our division. Right, so we have 0.21 times 0.52 divided by 0.6566. Right. And also keep in mind, I'm using this whole decimal because I have the whole decimal. I can use it. It's only 4 decimal places. I'm not using the approximation. Right. And that leaves us with 0.166. We'll round that one there. It's a lot more decimal places. Right. Or we have 16.6%. We could say approximately 17% if we're rounding to an approximate whole decimal or whole percentage. And there we go. what questions do you have? Hopefully after seeing these couple examples and stuff, it makes a little more sense on how to use these rules that we've explored the last couple lessons. All right. Excuse me. So here we go. Let's look at there, and once again, here's our course. Here's week 14. This is our discussion board for today. And as Matthew mentioned, essentially, we're doing another version of the problem we just did. Right? We have a computer company. It makes desktop and laptop computers at factories in 3 states, California, Texas, and New York. So you're going to have 3 original branches. California factory produces 40% of the company's computers, Texas 25%, 35% is New York. Of the computers made, 75% are laptops. Made in California, 75% are laptops. Of those made in Texas and New York, 70 and 50% respectively are laptops. So the 70% goes with Texas, 50% goes with New York. Right? So you have to use a little bit of deduction here to realize that 75% are laptops, 25% are desktops. Right? So you'll be able to fill in all your branches. All right? Question number 1, construct a tree diagram. Question number 2, find the probability the computer is a laptop. So probability of laptop. You're going to have to do very similar to the problem we just did. Given that a laptop is selected, what is the probability that it was made in California? Again, this is going to be incredibly similar to the problem I just did. So you might want to have like that available while you're working through this one. I'll have the notes all posted into the resources. Again, I recommend doing your work on paper and then upload the picture or file of your picture as the post.